About 1 more minute. All right, I think that's everybody. Stop me if you haven't submitted. Okay. All right, I'll end it here. We'll talk about these in a moment. I have some announcements first before we get started. So as usual, your chief homework, I'll post that later today or tomorrow, due on Monday. I have my office hour tomorrow at 2 p.m. We have class on Wednesday, and then I will not have office hours Thursday. We won't have recitation Friday, and we'll have remote classes Friday and Monday. So I'll be out of town Thursday to Monday. So just keep in mind, I won't have my office hour. We won't meet online for recitation. And then for Friday and Monday, I will post online lectures, and you'll be able to watch them at a time that works for you. I'll post an announcement on Blackboard when those are available, how to access them, and all of that information. But please write that down in your schedule that we won't meet in person Friday or a week from today on Monday. And then again, I'll update you through Blackboard announcement. So make sure you're reading those emails. I always check the box to send the announcement as an email to you all. So just make sure you're reading through those. I try to only include the most important information so it's not super long. But sometimes there's a lot of important information, so it ends up being long. But just keep that in mind. Questions on this? All clear? Okay. All right, going back to these iClicker questions. So we learned about solubility for a couple different types of solutes and solvents last week. And this question is all about water and what types of solute tends to dissolve in water. Now we have to remember properties of water and remember that like dissolves like. So water is a completely polar molecule. There's no nonpolar part of this molecule. There are 2 bonds and each one is polar. We've got a partial negative area by oxygen, a partial positive area by hydrogen. There's no neutral area. That's it. There's a partial positive, partial negative. Like dissolves like, so this means that polar solvents dissolve polar solutes. Polar solvents don't typically dissolve nonpolar solutes. So that would indicate that B, E, and C are all not options here because they all include nonpolar solutes. So water does not do a good job of dissolving nonpolar solutes. That's why oil, which is mostly nonpolar, and water, they don't mix together. So now the question is, can it dissolve both polar and ionic or just ionic? Well, we know that water itself is a polar molecule, so it can dissolve. It has a dipole. It can dissolve all other polar solutes. It also can dissolve ionic solutes because we have in water, there are the partial negative and partial positive areas. So the partial positive areas can interact with a negative ion, and the partial negative area can interact with a positive ion. So water tends to dissolve polar solutes and ionic solutes. An example of a polar solute is like ethanol, alcohol, that dissolves in water. An ionic solute, like table salt, that also dissolves in water. Then the next question is related to temperature. So now we're specifically talking about a solid dissolved in a liquid. And if the solubility of that solid increases as temperature increases, decreases, or it doesn't matter. Well, if we have an amount, we actually saw this with that last example we did on Friday, right? That was Friday? Yeah. Where we added some solid to a solution, only part of it dissolved, but when you heat it up, more of that solid dissolves. So the solubility of solids generally increases with increasing temperature. We also had this graph here that shows that for most of the solids here, with one exception, for most of the solids, solubility, which is the y-axis, increases as temperature increases. So that's the general trend. Yes, there are some exceptions, but we will focus on the trend here. So solubility of a solid dissolved in the liquid generally increases as temperature also increases. The opposite is true if we're talking about a gas dissolved in solution. Something like soda that has carbon dioxide gaseous molecules dissolved in the liquid, the solubility of the gas will decrease as temperature of the solution increases. Those gas molecules are gaining energy and they will escape the liquid and become vapor more so at a higher temperature than at a lower temperature. Okay, so in all of these examples, we're talking about a solute dissolved in a solvent. And we'll move to the next section, which is covering a few different ways that we can describe the concentration of a solution, or in other words, how much solute is present per a given amount of solution. So there are a few different ways to describe the concentration of the solution, and different methods are useful in different scenarios. Molarity we're most familiar with. We talked about that last term, and we have a slide on that. Molality, mole fraction are also common. Parts per million and parts per billion we won't talk that much about. These are useful for solutes that are in really low concentrations. And then we'll look at mass percentage as well. So we'll go one by one, do a couple learning checks as we go through. So molarity, y'all are familiar with this. Remember, this is the moles of the solute divided by the total volume of the solution. So moles per liter. This is convenient for describing liquid solutions. We're talking about the volume of something, and it's easy to describe the volume of a liquid. So molarity is often used for liquid solutions. But this is not convenient when we're describing solutions of changing temperatures. When a temperature of a liquid changes, let's say it's increasing, those molecules are gaining energy, and that liquid can expand and then occupy a larger volume. So the denominator, the volume of the solution, will increase, but you're not actually increasing the amount of molecules present, just the space between the molecules. So if you have a solution at one temperature and calculate its molarity, and then take that same solution, nothing's added or leaving, but you increase the temperature significantly, the volume of the liquid will change and you'll have a different molarity. So usually molarity is described at room temperature, and if you're changing the temperature of a liquid, this is not convenient. Molality is convenient when temperature changes because it doesn't include volume in the calculation. Instead of volume, we're looking at moles and kilograms. So this is the number of moles of a solute divided by the mass of the solvent only. So it doesn't matter if you're heating up the solvent or not, it will have the same amount of mass present. So it's okay to change temperatures to have the same molality calculation. The numerator is the same, still moles of solute. The denominator is different from molarity, where now we're calculating mass or kilograms of the solvent. And we use lowercase m for molality. We're going to take, in this next slide, we'll do a learning check. We're going to calculate molality. We're given a mass percentage. So we haven't gone to the mass percentage slide, but I will explain how to use that information, and we will calculate molality. So vinegar is a solution. It's typically 5% acetic acid. This is the formula for acetic acid. It's 5% acetic acid by mass. So that means for a total mass of solution of vinegar, 5% of that mass is acetic acid. And we are calculating molality. So let's remember molality is moles solute over kilograms solvent. So we have the mass percentage. We also know it says this is an aqueous solution. So water is the solvent. So when we're provided mass percentage, this means for any amount of the full solution, in this case, 5% of that is acetic acid. So we can convert that into useful values here. This is by mass, so we need a mass ratio. We'll use grams. But 5% acetic acid converting this to values, we can use 5 grams of acetic acid are present for every 100 grams of the solution. Let's use the same digit, 100.0 grams. So you could pick any value here that results in a 5% ratio. So 5 divided by 100, that will give us 0.05 or 5%. You could do 2.5 grams of acetic acid and 50 grams of solution. That will also give you a 5%. So this is a condition we're setting to work through the problem. You can have different values as long as they will still equal 5% by mass. So we're setting the condition that we're working with a 100-gram solution. Often that's needed for these questions. We'll do that again in another learning check. All right, so we have 5% by mass. So we're going to say we have a 100-gram solution, 5 grams of that is acetic acid. We'll take these values to then reach our calculations of the moles of the solute in the kilograms of the solvent. So we need kilograms of solvent. We have grams of solution. That's the total solvent and solute. So we'll use this equation here that mass, or I'll write kilograms, of the solution equals the sum of the kilograms of the solvent plus kilograms of the solute. So that will give us total mass of solution. We know that the total mass of the solution is 100 grams. That's what we're setting. So 100. I'm going to replace this, sorry, with kilograms. I'm just going to write mass because we can have different units here. So mass of the solution is the mass of the solvent plus the mass of the solute. So 100 grams solution equals mass of the solvent, so grams of the solvent, which we don't know yet, plus mass of the solute, which we set in that original fraction. So we have 5.0 grams of the solute acetic acid. So that means that the mass of the solvent is 100 minus 5, so 95.0 grams of H2O. So again, setting that original fraction, using those values with this equation to find the mass of the solvent. So we have mass of the solvent in grams. We need kilograms of the solvent for our denominator, so we can convert grams to kilograms. And we have mass of the solute in grams, but we need moles, so we'll do a molar mass conversion to get to moles of the solute. So molality is moles of, I already wrote that up there. So moles of solute, moles of acetic acid divided by kilograms of solvent. So I'll set this ratio. We have 5.0 grams of acetic acid in a solution with 95.0 grams of H2O. And then I'll do a series of conversions here to convert grams of solute to moles of solute and grams of solvent to kilograms of solvent. You could calculate those separately, just go from grams to moles, and then from grams to kilograms, and then do the division at the end. I'll put it all together into one large equation. But as long as you get to the same mole value and kilogram value, you'll be all set. So I'll convert to moles first. 1 mole of acetic acid is 60.05 grams. So this converts grams of acetic acid to moles of acetic acid. So we've reached the numerator that we're looking for. And then we need to convert 95 grams of the solvent to kilograms. 1,000 grams is 1 kilogram. So we've canceled out grams of water. And we're left with moles of acetic acid over kilograms of the solvent, which is water. So if you calculate this out, you should get 0.88 moles of acetic acid over 1 kilogram of H2O, or we can say that it's 0.88 lowercase m for molality. So when you look back here, remember that we set this original value. We picked 100 grams to make this calculation simple. So we did that first, and then used this relationship between the mass of the solution with the mass of the solvent and solute to find the mass of the solvent, and then we put our ratios together and do conversions as needed. Questions on this one? Yeah.
Is it supposed to be lowercase or big?
It's lowercase. Yeah, molality is lowercase. All right. We'll move to the next slide, which is another concentration unit, the mole fraction. These blanks here are insanely large. This is all we're writing, mole fraction. So the mole fraction, or capital X, without any units. So mole fraction does not have units. This is the moles of one component divided by the total moles of all components present. So since we are doing a fraction of moles divided by moles, we have no unit for mole fraction. This is useful when we have a solution with multiple solutes, because you can describe the mole fraction for individual solute relative to everything else that's present in the solution. This is common in gaseous solutions. Like the air, the atmosphere has nitrogen, oxygen, carbon dioxide, argon, a bunch of different gases. So we can describe the mole fraction of one gas relative to everything else that's present. So this is mole fraction, and then we have, what's next? Mass percentage next, and then we'll do some learning checks. So mass percentage, remember percentage means out of 100. For a mass percentage, you take the ratio of the mass of the solute, so the mass component in solution, divided by the total mass of the solution, so everything present. This is what we saw with acetic acid, where we had the mass of acetic acid divided by the total mass of everything that is present in solution. Now we multiply by 100 to make it a percent. All right, next learning check. This one will be an iClicker, so I'll get this open. So you are working with an aqueous solution of sodium chloride. The concentration is provided in milligrams per liter, and you're calculating molarity. So remember, molarity is moles per liter. You have one or two conversions to do to convert 0.075 milligrams per liter to molarity. When you submit on iClicker, just put in the numerical value. This one?
Yes. I think it must be so do post a PDF and yeah, try the PDF because that might be better. Yes, we divided by so, yes. And that was my next question. So it is a lot of conversion, but I understand never like.
Okay.
Like, I'm not sure how to.
So, okay, so, we know, this is similar to convert this to Instagram. Well, not okay. So when you're doing that, are you good, Zoe, on this? So, setting up a fraction review is helpful because as you go through, anytime you have some unit on the top and also on the bottom of another fraction, they get pulled out. But when you're doing the conversion, you have to use, like, the first one is what we start with. The next one, that's when both of us use uric acid. The one mole of uric acid is equal to 20.
That's the, I know that one. That's just HC. And then
And that's what we have to talk about. And then because we have to grab the uric acid first fraction, and the numerator, and then
So that's kind of similar to what.
yeah, so. Yeah. Yeah, so your first fraction would be 0.075 divided by the bottom will be 1/2.
Right, that's what that. So
So that you have to remember, but for this, like, milligrams is milligrams, so milligrams. Wait, it's the other, so it's 1,000 milligrams.
one, I got you.
So that would be fine, or you could do the 0.0000. I have to go Yes. Like 1 more minute. Maybe 1.5.
Yeah, but because it's just one, it's a vital that. You don't need to.
Yeah,
But this one's big right. Which is like not, this is.
Oh, so this, that was the earlier one. Okay, but that one will be.
Oh my God, never mind.
All right, let's go through that question. So it's not uncommon to be given the concentration of something in one concentration unit and need to convert it into another. So this is one example, and then we'll do another one on the next slide. So here we have a solution of sodium chloride. We have 0.75 milligrams per liter, and we're looking for molarity, which is moles per liter. So we need to convert units from milligrams to moles, and we're already set for the denominator. It's already in liters, so all good there. So 0.075 milligrams of sodium chloride. To end up with moles, and starting with mass, we need the molar mass to convert grams to moles. But to do that, we need to convert to grams first. So we're changing milligrams to grams. 1 gram is 1,000 milligrams. So this fraction here cancels out milligrams of sodium chloride. And then converting to moles, 1 mole of sodium chloride is equal to 58.44 grams. So now this fraction here cancels out grams of sodium chloride. And this is equal to 1.283 times 10 to the negative 6 moles of sodium chloride per liter, or 1.3 times 10 to the negative 6 molarity, just to use 2 sig figs here. But if you included more in your answer, it's okay. Questions on this one? Okay. We're going to go to this next one. So this one's a little bit more involved. One of the items of feedback that I got last term was to include more difficult learning checks or examples in class. So that's what this is. This will take a few steps to do the first and second parts of the question. So here we go. We've got concentrated sulfuric acid. Sulfuric acid is H2SO4. It's in water. So this is a H2SO4 in water solution. Okay. Okay, so sulfuric acid, H2SO4, concentrated sulfuric acid. This is a very high concentration. Sulfuric acid is one of those strong acids that we talked about last term. Quite dangerous. But 18 molar, so I think you can purchase it at this concentration. This is very high, but that would be a solution of sulfuric acid in water with a concentration of 18 molar. That solution, the water and sulfuric acid mixed together, has a density of 1.83 kilograms per liter. And we are going to first determine the molality and then the mole fraction. So we're going to do molality first. Remember, molality is the moles of the solute, so in this case, the H2SO4, divided by kilograms of the solvent. So that's H2O, this is H2SO4. Now, we're given 18 molar, that's a concentration of sulfuric acid in a liter of water. But this density is for the combination of both sulfuric acid and water together. That's not the density of just water. So we'll have to go through a few calculations here. So we know that the solution has this molarity. We know the density. We need to find, we're going to assume we have a 1 liter solution since we're given molarity. So we'll say we have 1 liter. We already know that in 1 liter we have 18 moles. So let me write this down. This is 18 moles of sulfuric acid per 1 liter of solution. We need to calculate how many kilograms of water are present in that 1 liter. So how much of the 1 liter is water? So just like we did before, we'll say kilograms of the solution equals kilograms of the solvent. So water plus kilograms of the solute, sulfuric acid. We're working under the assumption that we have a 1 liter solution. So we can calculate the kilograms of the solution because we have the density of the solution. So kilograms of solution will take 1 liter, multiply by the density, and that will give us the kilograms. So 1 liter times density, 1.83 kilograms per liter. So 1.83 kilograms of the solution. 1 liter solution weighs 1.83 kilograms. So we've calculated kilograms of solution. We're looking for kilograms of solvent. We can calculate kilograms of the solute because we know the molarity. So we know in a 1 molar solution there are 18 moles of sulfuric acid. So we can convert 18 moles to kilograms of sulfuric acid. So kilograms of solute so 1 mole H2SO4 in that 1 liter. We can convert moles to grams using its molar mass, 98.079. And then, so this provides the amount of H2SO4 in grams. We're looking for kilograms. One kilogram is 1,000 grams. So this is 1.765 kilograms of H2SO4. So remember, to get to molality, we need kilograms of the solvent. We've calculated kilograms of the solution, total mass, in kilograms of the solute. So of the 1.83 kilograms of the solution, 1.765 is the solute. So the rest is the solution. So bringing this equation back down, we have kilograms of the solution, 1.83 kilograms, equals kilograms of the solvent, which we're calculating, plus kilograms of the solute, 1.765. Subtracting 1.765 from both sides, kilogram of the solvent is 0.06. So this value I kept with more digits, but then didn't write it down with the extra values. So if you have more digits here, you'll calculate maybe 646, maybe 6457 or something like that. But it'll be a similar number there. Okay, so in 1 liter solution, we have 0.0646 kilograms of the water of the solvent. And we know that in 1 liter of solution, we have 18 moles of H2SO4. That's the molarity. That's what molarity tells us. So molality is 18 moles of the solute divided by total kilograms of solvent, 0.0646. .279 molality. So I just wrote at the top, we're assuming we are working with a 1 liter solution. We need that parameter to work within to do these calculations. And we picked 1 liter because that makes it simple. We already know there's 18 moles per 1 liter, 18 moles of H2SO4 per 1 liter. We're going to do the second part. I just have to add another slide to have more room. So 1 second here. It won't be as long for the second part. Questions on this first